This section covers the normal distribution. We'll talk about discrete distributions, continuous distributions. We'll review those. Then we'll talk more specifically about the normal distribution and how we can use the normal distribution. Then there'll be another video using Excel to show you how we work with the normal distribution using the Excel functions. So, as we mentioned in a previous section, a distribution describes all possible outcomes for a random variable and how likely each outcome is to occur. So we can think about this. It's easier to start thinking about discrete distributions before continuous, since we can actually list the outcomes, but we'll talk about all of that just a little bit. So a distribution is the most complete description of a random variable. As I said earlier, if you know the distribution, you know everything. What we typically do in samples is we describe the distribution in the sample. So just because you have plotted the distribution, in that you have a sample of data and you plot that distribution, you estimate descriptive statistics, you know a lot, but you don't know everything. So these descriptive statistics describe it, but it's not the complete picture. So we typically use the mean, the median, the standard deviation. These gives us the mean and median tell us where the distribution is located. The standard deviation tells us how spread out that distribution is. So if it's wider or narrower. Skewness tells us about how symmetric the distribution is. Kurtosis tells us information about how thick the tails are, so how likely are extreme values or values far from the mean. But even though we know 1, 2, 3, 4, 5 different properties of the distribution in the sample, we may not have all the information that we need. So discrete and continuous random variables have distributions, but the properties are different. So the way we view them, the way we work with them, it's a little bit different, but the idea is the same. The what outcomes are likely and how frequently we expect them to occur. So a discrete random variable is something that can take on specific values that are known and countable. So there can be a lot of values. It doesn't mean there are only a few outcomes. It just means the outcomes are known and countable. So how many customers per day visit your store, the number that shows up on a die when you roll it, when you flip a coin, do you get heads or tails? Those are discrete random variables. So we would assign a number to each outcome on the die roll. We could assign heads, tails, and we could look at the probability of getting a heads, probability of getting tails, and so on. The number of customers per day, you may have thought about in a previous stats class, the Poisson distribution. So the Poisson distribution is what tells us, the Poisson distribution is used when we're trying to estimate the number of times something might occur in a fixed interval. So if the interval is a day, how many customers do you get per day? That's a Poisson distribution. That's not something we're going to cover in this class, but that's another discrete distribution that you may have worked with in the past. So we're going to look at an example of a die roll. So we're going to roll a die. The sample space is the set of all possible outcomes. So this S represents the set of all possible outcomes when we roll a die. You can get a 1, a 2, a 3, a 4, a 5, or a 6. Those are the only outcomes that are likely. We're going to ignore these bizarre cases where maybe it just happens to land on its edge. We're going to ignore that. So these are the only outcomes that can occur. And this is the probability that each outcome occurs. So if it's a fair die, you will get a 1 with probability 1/6, a 2 with probability 1/6, and so on. And if you add all of these up, they add up to 1. Because if you roll the die, you will get a 1 or a 2 or a 3 or a 4 or a 5 or a 6 with probability 1. No other outcomes are likely. So this f of x, this is just the probability of observing a specific outcome. So we would say 1/6 is the probability of observing 1. 1/6 is the probability of observing 2. So those are the outcomes that go with, or the probabilities that go with each particular outcome. If you flip a coin, the sample space is heads or tails. Again, we're ignoring the case where the quarter could land on its edge. So these are the only two outcomes that occur. The outcomes heads occurs with probability 1/2, tails with probability 1/2, assuming it is a fair coin. So once we have this idea of a distribution, so we know what outcomes are likely, what outcomes are possible, how likely those outcomes are to occur, we can start thinking about expected value, which is what is the mean of that discrete random variable. Just because it's the expected value or mean of a discrete random variable, it doesn't necessarily mean we're going to get a value that's even observable. It's simply a weighted average. We talked about averages in the previous section, or the sample mean. We'll think about it in a little bit more detail here and where it actually comes from if we have a discrete random variable. So it's a little bit of notation, a little bit of math here, but don't worry about this. We're going to do it all in Excel. If a discrete random variable can take on the values x1, x2 through xn, and we can assign probabilities to each one of those outcomes, then the expected value of that discrete random variable is just the outcome multiplied by the probability that we observe that outcome. So if we're thinking about a die roll, let me just go down here to the bottom. The expected value of a die roll is outcome 1 times probability 1/6 plus outcome 2 times probability 1/6, and you keep doing this. When you add that up, you get 3.5, which seems a little bit odd because 3.5 is not a number that can actually show up when we roll a die. But that's the expected value of a die roll. So it's a little bit harder with heads and tails because we don't really assign numbers to heads and tails. But in general, if you want to estimate the expected value, we're going to list the possible outcomes, multiply each outcome by the probability, and then you add those up. And that's going to give us the expected value of a discrete random variable. We can also do this with continuous random variables, but it's a little bit more complicated. So this is something we'll do these calculations in Excel. So, but this is the more formal way of defining what expected value actually means. So most of what we're going to do in this class will be with continuous distributions. So we'll talk about discrete distributions a little bit more in the future in specific examples, but the data that we're going to be working with is primarily continuous, so this is what we'll be spending most of our time thinking about. So stock returns are continuous. They can take on any value, in theory, between negative 100% and positive infinity. So it can only lose it. It can go to 0, which means that there's a 100% negative return, or it can go up as much as it possibly can. The body mass index is continuous. How long it takes to fly somewhere. These are all things that are continuous. And there are 3 different ways we can describe a continuous random variable. So with a discrete random variable, we can plot it. We can do those things as well. But it's pretty easy just to look at the distribution if it's discrete. If it's continuous, there are a couple things we can do. A frequency table, which I was showing you earlier in Excel. We can make a pivot table, and then we can plot. We can see how likely each outcome is to occur. When we're working with a continuous random variable, we have to make bins because we don't want to think about the probability that each specific outcome occurs because each specific outcome only occurs once, typically, if it's continuous. So we'll make frequency tables and we'll generate bins of a certain width, and then we'll use that to count the frequencies. The density function, these are a little bit harder to work with because it requires some calculus to generate the, we need calculus if we're going to work with the density function. And then the density curve is just a graphical representation of the density function. So we can estimate the expected value of a continuous random variable. It's a little bit more complicated than in the discrete case because it does require us to use calculus. So this variable x that I generated for this table is normally distributed with a mean 0 and a standard deviation of 1. So it's a standard normal random variable, which is something you would have seen in a previous statistics class. But this is a frequency table. So we can't put specific values because the probability we observe a specific value is effectively 0 if it's continuous. Because we have an infinite number of possibilities, the probability we observe one particular one out of an infinite number is 0. So we make these bins. So this says the probability that we observe an x that's less than negative 3.5 is 0.0002. This tells us the probability that we observe an x between negative 0.5 and 0 is 0.1915. 0 to 0.5 is the same. And if you notice this distribution is perfectly symmetric. So if you look at less than negative 3.5, that's the same as greater than positive 3.5. And it's because we're working with a normal distribution that is perfectly symmetric. But this is a frequency table. We set up a range of values and we figure out how likely is it, what's the probability of observing something within that range. You can check for symmetry. As in this specific case, we can identify the mean because we know, I told you that it's just standard normal. So mean 0, standard deviation 1. But it's harder to estimate the means and the variances and the different descriptive statistics from a frequency table because we have gaps. And depending on how big the gaps are, the width of the bins, your answer might change. Even though the true answer remains the same, your answer may appear to change because you're using different bin widths and different things. So we will use this mostly to get ourselves to a plot. So we'll make a frequency table, but the frequency table will be used to generate a histogram that we can use to check for normality visually. The density function is very, very precise, but also very difficult to work with. So this is the density function for the normal distribution. The normal distribution can be described with two parameters, mu, which is the mean, and then sigma, which is the standard deviation. And I'll talk about these a little bit later. I'll have some examples on what happens if we shift mu or sigma and how that actually changes the underlying distribution of that random variable. So if we know this, we know everything. We can use this function to generate the mean, the standard deviation, the skewness, the kurtosis. We can get all of those things using this distribution, but it does require a little bit more calculus. If we have a variable that's normal, the mean is mu, standard deviation sigma, skewness is actually 0, and excess kurtosis is 0. So these are properties of the normal distribution. The actual kurtosis is 3, but the excess kurtosis is 0 because that's what Excel computes. So when you estimate kurtosis in Excel, excess kurtosis tells you how much more or less kurtosis it has compared to the normal distribution. So are the tails thicker or narrower than the normal distribution? Again, this is complete. This is a complete picture of that distribution, but it does take a little bit of calculus to actually understand, to work with this, to work with the density functions. And it's also important to understand that this is a model. This is theoretical. So we often say, oh, this is normally distributed. Test scores are normally distributed. Height is normally distributed. Weight is normally distributed. Those are assumptions. The normal distribution has a range of, or a support of negative infinity to positive infinity. So if something's truly normally distributed, in theory, you can observe things as small as negative infinity and as large as positive infinity, even though the probabilities assigned with those events are really, really rare. So with a normal distribution, most things occur within about 3 standard deviations of the mean, but in theory, it can be positive infinity to negative infinity. So when we say something's normally distributed, we are making an assumption that it's normally distributed, because very, very, very few things in this world are truly normally distributed in the population. So the density curve is just the graphical representation of the density function. So if I plot this function, I would get a density curve. And the normal distribution is that bell-shaped distribution that you've probably seen before, where it's centered at mu. So mu is the mean of the random variable. And notice that's exactly in the center of that distribution, and it's perfectly symmetric. So a density curve is just the graphical representation of that function. If we change mu, the curve shifts to the right or to the left. If we change sigma, it gets flatter or wider. But all we're doing is describing that density function. There are a couple important properties of the normal distribution. Actually, of any really this one's true for everything. The area under the curve is 1. For something that's symmetric, like what we have right here, the probability that x is less than mu is 0.5. So the total area under that curve to the left of mu is 0.5. The area under that curve to the right of mu is 0.5 as well. And the probability that x is greater or equal to some value. So this is just some value x naught, some arbitrary value. The probability that we observe something that's greater than this is just 1 minus the probability that something is less than this. Because if we think about this arbitrary value x naught, the only possibilities are it can be less than or equal to that, or greater than that. Equal to is effectively 0, so it doesn't really matter if we have the inequality there or not. It's just there for completeness. The probability that we observe something greater than that has to be 1 minus the probability that we observe something less than that, because the total area under the curve has to add up to 1. And I'll show you some examples of what that means a little bit later. So if we're using the normal distribution, there are 2 ways we can use it, but a couple different questions we can answer when we're working with these problems. So the first is, what's the probability that we observe something less than the specified value? So if we have some normal distribution with mean mu and standard deviation sigma, what is the probability that we observe an x value that's less than x naught? So this is the Excel function that we'll use to estimate that probability, and I'll show you all of that in the lab videos a little bit later. We can also find, for some arbitrary value x naught, what's the probability that x is greater than that? And using this property right here, the way we find the probability that x is greater than some value is by taking the probability that it's less than that and then subtracting that from 1. So the default in Excel, by default, Excel tells you the probability that x is less than something. If we want to know the probability that x is greater than something, we have to do 1 minus that norm.dist function. So this part right here tells us the probability that x is less than x naught. 1 minus that tells us the probability that x is greater than that. And the last thing we can do is find the probability that x falls between 2 values. So what is the probability that x falls between some lower bound and upper bound? So what we have to do, since Excel by default tells us the probability that x is less than something, we find the probability that x is less than the bigger number, and then we subtract the probability that x is less than the smaller number. So if we do norm.dist on the upper bound, it's going to give us the area under the curve to the left of this value, but notice that includes all of this area down here. We don't want that. So if we only want the area in between, we find the area that's under the curve to the left of the biggest number, and then we subtract the area under the curve to the left of the smaller number. And that will just leave us with the area in between. but always do the big number first and the smaller number second. If you mess this up and you get a negative and if your answer is negative, then you need to just flip it around because probabilities have to be positive. The norm dot inverse function is what we use to find values that correspond to probabilities. So in these previous problems right here, I give you an x value and I ask for a probability that's associated with that x value. With this type of problem, I give you the probability and ask you to find the x value that is associated with that. So let's say I'm asking you find x naught such that the probability that x is less than that is equal to alpha. So if you have something with a mean mu and standard deviation sigma, so you know the mean and standard deviation, I can ask you to find the x value such that the area under the curve to the left of that value is equal to, for example, 0.05. This would be the equivalent of finding the 5th percentile for that variable. I could also ask you to find the x value that corresponds to the top 10 percentile. So let's say I want to know what's the value such that only the probability of being greater than that is 0.1. So you're trying to find a value that's bigger than about 90% of the values so that only 10% of values are greater than that number. So let's say we have a program where everybody takes a test, and if you score in the bottom 25th percentile, you get dropped from the class. So what I want to do, I'll take all the test scores. I will figure out what's the test score such that 25% of the class did worse than this. That's what this type of problem right here is. Or let's say we have an exam, and anyone who scores in the top 10% gets $1. If you score in the top 10%, I'll give you $1. So I'm going to take all the test scores. I'm going to find the test scores such that only 10% of students did better than that number. That's this type of problem right here. I'm going to set the probability and then find the x value that corresponds to that probability. And we'll do all this in Excel. We often assume normality, so it's important to check for normality, at least informally check for normality, because it may or may not be a great assumption. So if something is truly normal, the mean and the median are the same. So in the normal distribution, the mean and median are the same because it's perfectly symmetric. The skewness and kurtosis are also close to zero. Or actually, if it is a normal distribution, skewness and excess kurtosis will be equal to zero. But in the real world, things are not perfectly normal. So we want mean close to median, skewness and excess kurtosis close to zero. And if those things hold, we have some confidence that the normal distribution, or I don't say some confidence, it's maybe reasonable to assume the normal distribution when we're making inference. There's also this rule that you may have heard of before, that if something is truly normal, 68% of values should be within one standard deviation of the mean. So if you look at the mean plus or minus one standard deviation, that should catch about 68% of values. The mean plus or minus 2 standard deviations should catch about 95% of the values. And the mean plus or minus 3 standard deviations should catch about 99.7% of values. So if we observe something that's more than 3 standard deviations away from the mean, that's a pretty rare event. It's unlikely to observe things that are 3 standard deviations above or below the mean. And all that really means is if we go back and look at this density function right here, if we look at the mean plus a standard deviation minus a standard deviation, we're looking at values. Actually, let's just go back to this one right here. Because we know the standard deviation here is 1. So this data is normal with a mean 0 standard deviation of 1. So if you take these probabilities right here and you go from -1 to 1, so if we're going to go from here to here. So if you add up those probabilities, you should get a number that's pretty close to 0.68. Because the probability that we observe something between -1 and 1 should be about 0.68. If we go from -2 to 2, and you add up those probabilities, we should get something that's pretty close to 0.95. And if we go from -3 to +3, we should get about 99.7. Is that right? Let me double check that number. Yeah, we should get about 99.7% of observations should fall within -3 to +3 standard deviations. So that's what that rule means. It's telling us how the proportion of observed values that we expect to be within a certain range of the mean, if it's truly normal. So if you look at that and you don't get, and these numbers aren't really matching up, it's because the normal distribution doesn't accurately describe that distribution. You can remove outliers and check again, but just be careful with that step. I'm always hesitant to throw out data when it's good data. If you have small samples, outliers are a big problem. But if your sample size is sufficiently large, it's going to be less sensitive to these outliers. Kurtosis risk, again, kurtosis tells us how thick the tails are. So if you incorrectly assume the normal distribution, you may underestimate how likely extreme values are. So if you're thinking about returns and you know something has a average return of 3% and a standard deviation of 2%, you take that information, you apply the normal distribution, you're going to get a certain amount of, you're going to estimate the probability that you get a large positive or negative return, but you may underestimate how likely that actually is to occur because you incorrectly assumed the normal distribution. If it has thicker tails than the normal distribution, you're going to underestimate those extreme events. And if you have an extreme positive event, that's not a problem. If you think, well, the average return's 3% and I got 19%, awesome. That's great. But if you assume 3% and you get -15%, you're not going to be real happy with that. So you may incorrectly assign risk if you apply the normal distribution when you shouldn't apply the normal distribution. So here's a quick example. This is older data. This isn't the most recent data for Tesla and Microsoft. We just want to look and kind of do a quick check for normality here. So we want the mean to be close to the median, and we can see with Tesla they're not even close. The mean is not close to the median. For Microsoft, they're reasonably close. Again, there's no specific rule for how close is close enough. But just looking at this, Microsoft's much closer than Tesla. Skewness and kurtosis, again, there's no set rule for what is close and what's not close. But we can see that Microsoft is much closer to 0 than Tesla on the skewness and excess kurtosis. So if you're just looking at this, maybe the normal distribution is an appropriate assumption for Microsoft, but maybe inappropriate for Tesla. And I think the best way to check for normality is just do the eyeball test. Take a look at the returns and see how well the normal distribution approximates that data. And if you're looking at Tesla, this is using, so what this green line is, this is what we would observe if it were truly normally distributed with the mean and standard deviation that we observe for Tesla. So if we assume that this mean and this standard deviation are true and it's normal, this is the distribution that we would get. And we can see that that doesn't perfectly, it's never going to be perfect, but it doesn't really do a great job describing Tesla. Where with Microsoft, a lot of the values that we observe seem to fall pretty close to that underlying normal distribution. So making inference about Tesla using the normal distribution may not be as accurate as the inference that you would make about Microsoft using the normal distribution. If you notice with Tesla, we have these extreme values up here, and this is why that skewness is positive, is larger and more positive, because it's pulling that mean value above the median. So notice the mean return is much larger than the median. It's because these extreme values are pulling up the mean. But if you trim these extreme values, this distribution would shift to the left a little bit, and it would be a more reasonable approximation. So this is what we're talking about with remove outliers and check it again. It could be that these outliers are the reason the mean of the normal distribution isn't perfectly matching up with kind of where the largest mass of the actual observed values fall. So Microsoft looks approximately normal. Assuming Tesla returns are normal may be a poor assumption and may lead to some imprecise inference. So I'll follow this up with a video in Excel showing you how to use the normal distribution and how to work with the functions in Excel for the normal distribution.